Hello everyone, welcome to another lecture as part of our ME 6151 Computational Heat and Fluid Flow course. So in the last lecture, what we saw was we discussed about up-wind difference scheme, which was said to be an alternate for the central difference scheme, right? And we also looked at the order of accuracy of the two schemes that we have studied, that is the CDS and the UDS. And we have also looked at an example problem. So this was a pure convection problem, but this was a steady pure convection problem, right? And then we noted that if we have a pure convection, when we try to solve using central difference method, what we got was some kind of wiggles were obtained as compared to the exact or correct solution. And we tried to solve with upwind difference scheme. Then what we noted was we got dissipation or diffusion in the solution, right? Although there was no diffusion in the original problem, we saw that we got some diffusion because of the way the upwind difference scheme kind of works. Okay, so we noted these two aspects. So in today's lecture, as to continue from where we left off, what we're going to look at is we're going to look at numerical diffusion and dispersion. That is basically this artificial diffusion and dispersion that are obtained because of UDS and CDS. Okay, so we're going to see this from a numerical perspective. Okay, so this we're going to analyze from numerical perspective. So can we see this kind of behavior, or can we explain this behavior from the equations that we are solving? Okay, so that is what we're going to analyze today. And depending on the time, we are also going to look at how unsteady convection equation looks, and what can be done in order to solve unsteady convection using again these two schemes that would come in the later lectures. Okay, so then let's go into the lecture. Essentially, so the example problem on pure convection, right? So this was what we studied in the last class, example problem on steady pure convection. We noted that we have the central difference scheme produced oscillations, which we called it as a dispersive scheme, and the upwind difference scheme produced diffusive solution, right? It kind of smeared out the sharp peaks that we have in the solution. Okay, so that's what we kind of noted. Now, can we explain this behavior using model equation? So today we're going to see how to construct this model equation, or also known as modified equation. Okay, so we will explain this behavior of dispersion and diffusion using a modified equation, or also known as equivalent equation. Okay, so these are equations which are written from the original governing equation. Okay, so we're going to see how to construct these modified equations or equivalent equations for a given equation and see if we can explain the behavior. Okay, so that is the agenda for today. Then let us start off with pure convection problem. Again, this is a steady pure convection problem. Okay, so we have del dot rho u bar phi equals 0. Now if we consider two dimensions, then nabla can be expanded in two dimensions. This would be partial x rho u phi plus partial y rho v phi equals 0. Okay, then for the sake of simplicity, I'm also going to consider density equals constant. So rho equals constant, and I will also assume that u bar, which is u I hat plus v j hat, is also a constant vector, and the two velocities in the x and y directions are also positive. Okay, so we're going to assume that u is a constant and v is a constant, and these two are positive constant. That means u and v are constant and they are also greater than 0. Okay, so that's what we're going to assume, because then we can simplify this equation very easily. Okay, so with these assumptions, the first step is to, in finite volume method, is to integrate the governing equation on a control volumes, and we can write this as a control volume del dot rho u bar phi dv equals 0, right? And if we apply Gauss divergence method, Gauss divergence theorem, and then also convert the resulting surface integral into a summation, then we can convert this equation into sigma f rho u bar phi f dot af bar equal to 0. Okay, so that is the resulting equation we can write. Okay, all right, then we have to choose a particular method here now, right, a particular scheme in order to essentially further discretize this problem. Okay, so then we will use, so if I go back, then essentially what we have is rho u bar phi f dot af bar. Then this can be expanded for each of the coefficients, right, each of the faces, that is east, west, north and south. Okay, then this can be written as fe phi east minus fw phi west plus f naught phi north minus f south phi south, right. This is already what we saw in the last lectures. Because fe, the way fe and fw are defined is basically it is rho u e delta y, but now we have assumed that u is constant everywhere and v is constant everywhere, so rho u e equals rho u w, right. As a result, both the flow rates are the same, rho u delta y, right, both are the same, and this minus comes in because of the area vector being minus delta y I cap for the west face. Okay, so that is the reason here. Now what about the f north and f south? F north and f south are again are both equal to rho v delta x, because v is a constant and it is positive. Okay, so as a result we can simplify this equation further, and also that means we can kind of write this as fe or rho u delta y times phi east minus phi w plus rho v delta x times phi north minus phi south, right. That can be written, and if I choose, let's say, upwind difference scheme, if I choose upwind difference scheme, then what we can do is we can again write the upwind differencing for the phase value of phi. That means depending on the flow rate we would use upwind for the dependent variable. Okay, and because we have assumed that u is greater than 0 and v is greater than 0, we can now write phi on the phase east phase equals phi for capital P, right, because u is greater than 0. Similarly, phi little w on the west phase, because u is greater than 0, will be equal to phi capital W. Okay, applying the same logic, phi on the north phase can be written as phi sub P, because v is greater than 0, and phi on the south phase is equal to phi capital S, because v is greater than 0. Okay, so now this can be written. Then we can go and substitute for these phi east, phi west, phi north and south into the equation number 1 here and collect all the terms. Then we can write this as rho u delta y phi p, right, instead of phi east we wrote phi p, minus rho u delta y instead of phi little w we wrote phi capital W, plus rho v delta x phi north instead of phi north we wrote phi p, minus rho v delta x phi little south, and replacing that with phi capital S equal to 0. Okay, so this is the equation 1, which is modified with these upwind difference scheme and also substituting for the corresponding flow rates. Alright, now let us divide this entire equation using delta x times delta y. Okay, and then we can write this as rho u delta y divided by delta x delta y. So 1 delta y gets cancelled and you would get delta x in the denominator, and then what you get is phi p minus phi w by delta x, plus from these two terms we would get rho v times phi p minus phi capital S upon delta y equal to 0, right. That's what we get. Now look at this equation. So let's call this equation as 2. Now what we do is, well, up till now what we have done is you have taken the original governing equation and applied the corresponding discretization scheme. In this particular case it was upwind difference scheme, and we have just written the finite volume linear algebraic equation, right. This is the discrete equation for pure convection using upwind difference scheme. That's all we have done. Now in order to construct a modified equation, what we have to do is we have to rewrite this equation by expanding some of these phi values using Taylor series expansion. Okay, so in this what we see is we have three quantities, phi p, phi w and phi s. Okay, so I'm going to expand phi w and phi south about phi p using Taylor series expansion. Okay, so let me expand phi w and phi south about phi p. Then I can write phi capital W as W is to the west of phi P or location xp by minus delta x, right? It is about delta x to the west of P, right? As a result, phi W can be written as phi P minus delta x partial phi partial xp plus delta x square by 2 factorial partial square x partial square phi by partial x square minus delta x cube by 3 factorial partial cube phi by partial x cube and so on, right? That is expansion for phi W. Similarly, phi S can be written. Phi S can be written in terms of phi P being in the delta y direction to the south of location P, right? We can write phi south as phi P minus delta y partial phi partial y plus delta y square by 2 factorial partial square phi by partial y square minus delta y cube by 3 factorial partial cube y by partial cube phi by partial y cube and so on, right? So that's what we have for Taylor series expansion of phi W and phi S quantities. All right. Now, in order to, we essentially want to replace this quantity as well as this quantity using the Taylor series expansion we have. So if we want to write phi P minus phi W, so we divided by delta x, so we can write this from here. Essentially phi P minus phi W, that would give you this entire term sent to the left hand side, but then we want to divide by delta x, right? So what would remain for phi P minus phi W divided by delta x? That would be essentially, if I go back and make it continuous, okay, so essentially phi P minus phi W by delta x would be partial phi partial x, right, minus 1 delta x gets divided, so this will be delta x by 2 partial square phi by partial x square, then this will be plus delta x square by 3 factorial partial cube phi by partial x cube, right? So that's what we have. That means phi P minus phi W by delta x equals partial phi partial x minus delta x by 2 factorial partial square phi by partial x square plus delta x square by 3 factorial partial cube phi by partial x cube, right? Essentially we just rewritten what is this quantity from the first equation that we have here. All right. Similarly, can we write what is phi P minus phi S by delta y from this equation? Yes, we can write that. That means send phi S to this side and send all these guys to the left hand side and divide by delta y, right? What we remain is partial phi partial y, so that would be partial phi partial y minus, similar to here, we will get delta y by 2 factorial times partial square phi by partial y square plus delta y square by 3 factorial partial cube phi by partial y cube and so on, right? So essentially we got expressions for these two quantities, right, from Taylor series expansion. Okay, so we have these two quantities. Now what we do is we just substitute for these two quantities in that equation, right? So essentially the equation is what was the equation? Equation was rho u times this quantity plus rho v times this quantity. Okay, so that means rho u times partial phi partial x minus this delta x by 2 factorial blah 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 plus we have rho v times partial phi partial y minus delta y by 2 factorial, so partial square phi by, this should be partial y square, right? This should be partial y square, and this is delta y square by 6 partial cube phi by partial y cube and so on equal to 0, right? So essentially we got now one equation which is again a continuous equation, right? So this is a continuous equation, right? This is essentially, it is taking care of the terms which we have, which we would probably neglect because of the discretization, right? Those terms are now substituted back. So we got some continuous equation from the discrete equation that we have constructed. Okay. All right. Then if you look at what is if I rearrange these terms, then I can write rho u times partial phi partial x plus rho v times partial phi partial y. We have these two terms, and I would like to send the remaining quantities to the right hand side. That would be rho u delta x by 2 times dou square phi by dou x square plus rho v delta y by 2 dou square phi by dou y square right, plus order delta x square plus order delta y square and so on, right? So we get so many of these terms, right? So we got now an equation which is actually the modified equation, but we would like to do some more simplification before we call it a modified equation. Okay, so in order to make things little more simple, what we do is let us assume that u and v are not only constant but they are also equal. Okay, they are positive and they are also equal. Okay, and then let us also assume that we have a uniform mesh in both the directions, that is delta x equals delta y. Okay, these are basically a couple of simplifications to make the analysis easy. All right, then we can write this equation as rho u partial phi partial x plus rho v dou phi dou y equals, because these two rho u delta x by 2 and rho v delta y by 2 are now one and the same, because u equals y and delta x equal delta y, I can write this as, combine these two quantities, we can write this as rho u delta x by 2 times partial square phi by partial x square plus partial square phi by partial y square plus order delta x square. Alright, so this equation is what we call as the modified equation. Okay, so we call this as the modified equation or model equation or the equivalent equation. Right, now how did we construct this? Essentially we started off with the original equation, right? Start with the original equation, then write the corresponding discrete equation, right, for the finite volume method. Then in the discrete equation use Taylor series expansion and then rearrange, right, so that it looks similar to the given equation, right? Okay, so now why do we say this is similar? Okay, it is similar because we were started off to solve a pure convection equation in 2 dimensions, right? Now that means I can, because rho u v are all constants, I can take these guys inside the derivative. I can write this as partial x times rho u phi plus partial y times rho v phi equals, on the right hand side again these are all constants. I can now write this as, instead of rho u delta x by 2 dou square phi by dou x square, we can write this as partial x times rho u delta x by 2 times dou phi dou x plus partial y times rho u delta x by 2 times partial phi by partial y plus, of course, we have order delta x square terms here. Okay, now we can of course rearrange this as del dot rho u bar phi equals del dot this quantity rho u delta x by 2 times grad phi, right? We essentially converted this equation into a vector equation that looks like this, right? Okay, now so this is basically something similar to what we have learned. This is basically the convection term, this is the diffusion term. But this is not something that we started off to solve, right? We started off, or we wanted to solve pure convection equation where del dot rho u bar phi equals 0, right? Whereas what we ended up with is this equation 3, which is not the same equation, rather this is the equation, right, or the continuous equation that the finite volume method or the method that we have employed will solve, right? So this is the equivalent equation that the method solves, right, which is not the same as what we wanted to solve. Okay, now why is this coming? This is happening because of the discretization scheme that we have chosen, which was the upwind difference scheme, right? What does this look like? So essentially there is a diffusion part in there. So although we wanted to solve pure convection, we have some diffusion coming into play. That's why when we looked at in the last lecture, there is some diffusion of the smearing out of the sharp discontinuities was occurring. Right now, what will be the effective diffusion coefficient? The effective diffusion coefficient is equal to rho u delta x by 2. This is more like gamma, right? This is more like gamma. So that means there is some diffusion, which we call it as numerical diffusion, okay, which is coming into play because of because of the upwind difference scheme that we have chosen, and the artificial diffusion coefficient is not a constant, rather it is equal to rho u delta x by 2, right? That means if we try to solve pure convection using UDS, it will be diffusive. However, the diffusion coefficient is proportional, right, to delta x. That means if we take smaller and smaller delta x, then the gamma effective can be taken to go to 0, right? But it will never be 0. It can be made to go to as small as possible, right? So as a result, this can be made small, but it will never be 0, right? It will never be 0 because it is always proportional to delta x. Fine. So, but that kind of gives us some insight on why the upwind difference scheme is diffusive, right? Like what we have observed yesterday. Now, in general, not only upwind difference scheme, but any method that we use, if it gives in the modified equation, if it gives this kind of even order derivatives, okay, if it gives even order derivatives, then that method can be said to be, that means if you have in the equivalent equation the even order derivatives such as these guys, dou square phi by dou x square, second order derivative, then we can call this equation or that particular equation as always diffusive, right? So in the modified equation, if the derivatives are of the second order, fourth order, sixth order, and so on, then that scheme can be called as a diffusive scheme, right? It produces diffusion. Now, what will be the order of accuracy of this method? Order of accuracy is, of course, first order, because this is the truncation error, right? That means this is order delta x. So the method is first order accurate, but it is diffusive. Okay. All right. So then let us look at now the other scheme that we have tried solving the pure convection equation, that is the central difference scheme, right? We would use the CDS scheme to solve for pure convection problem. Okay, and essentially we want to also construct what is the modified equation for a pure convection problem, using the central difference scheme, right? So that's what we want to do. All right, then let us again get started with the pure convection, that is del dot rho u bar phi equals 0. Right, the right hand side del dot gamma grad phi and s phi is equal to 0 anyway, and then we again assume that density is constant, so rho is constant. When the velocities u and v, the two components of velocity, are also constants and they are greater than 0. Okay, that's what we assume, and we apply finite volume method and then transform this equation into a discrete equation, right? So the discrete equation reads like this: Fe phi E minus Fw phi W plus F naught phi naught minus F south phi south equals 0. Okay. Now, in this one, again Fe and Fw are both equal to rho u delta y, and F naught and F south both are equal to rho v delta x, right? Because we assume that u and v are constants. Their value on the east face is the same as west face and everywhere else. Same for the v, the value is same on the north face and the south face and everywhere else. Okay. Then what we get is, we get rho u delta y times phi little e minus phi little w plus rho v delta x times phi little north minus phi little south equals 0. Okay. So this is our equation by substituting for the flow rates in terms of the rho u delta x, rho u delta y and rho v delta x. Okay. Now we have to introduce the discretization for the central difference scheme, right? That is basically, how do we say phi little e is what, how do we describe the value of phi on the east face, right? This is using central difference scheme. We write it as the linear average or arithmetic average of the two cell values, right? So in the CDS, what we said is, we say phi little e equals phi capital E plus phi p by 2, and similarly phi little w equals phi capital W plus phi p by 2, and phi little north equals phi capital north plus phi p by 2, and phi little south equals phi capital south plus Vp by 2, right? So we have the central difference scheme definitions. Then we will plug it into this equation. What we see is that phi little e as E and P, and phi little w, which is coming with a minus, has W and P as well. That means the P gets cancelled, and what we get is, instead of phi little e minus phi w, we get phi capital E minus phi capital W by 2, right? So this equation is nothing but rho u delta y times phi capital E minus phi capital W by 2 plus rho v delta x times phi capital N minus phi capital S by 2 equals 0. Okay, so that's what we have. Then let us again divide throughout by delta x times delta y. Then this delta y gets cancelled, and then we get a delta x in the denominator, and we also get a delta y in the denominator because this delta x gets cancelled. Alright, then what we can do is we can write the final equation. This is as rho u partial phi e minus phi w by 2 delta x plus rho v times phi north minus phi south by 2 delta y equals 0. Okay, so this is the discrete equation, right, using central difference scheme. Okay. Now what you see is that, of course, this was derived using finite volume method, but what you see is that this would be the same as the equation that you would if you had used a finite difference method, right, and substituted directly for partial phi partial x in terms of a second order central difference scheme as well, right? Okay, that would be the same. All right, so that's what you would note from here. This equation would be the same even if you have started off with a finite difference method, because right now we have assumed a lot of things to be constant and stuff like that. Okay, that's why we could write, and eventually it looks similar to the central differencing scheme coming from a finite difference method, right? Okay, so equation 5 is our final discrete equation. Now what do we do in order to construct a modified equation? What we have to do is we have to plug in for phi capital E, phi capital W, phi north and phi south in terms of phi p, right? That's what we have to do in order to construct the modified equation. So therefore, let me expand phi east and phi capital W using Taylor series about phi p. So what is phi capital E? Phi capital E is nothing but phi E is at delta x from phi p. So phi E equals phi p plus delta x times partial phi partial x plus delta x square by 2 factorial dou square phi by dou x square plus delta x cube by 3 factorial dou cube phi by dou x cube, and so on. Similarly, phi w would be equal to phi p minus delta x times partial phi partial x plus delta x square by 2 factorial partial square phi by partial x square minus delta x cube by 3 factorial partial cube phi by partial x cube, and so on. Okay, so that's what we have written for this quantity. So can we write what is phi e minus phi w by 2 delta x from here? Yes, we can write. That will be this minus this divided by 2 delta x. That would give you phi p gets cancelled, right? So essentially this guy gets cancelled, right? And then these two would e minus w, this would add up to 2 delta x, but that's what we are dividing with. So what remains is partial phi partial x remains. Then what about this guy? This guy also, this is a plus, so this guy also gets cancelled, right? This guy gets cancelled, these two gets cancelled. Then this guy will become delta x cube by 6, but you are adding them up, so this will become delta x square, right, divided by, we are also dividing by 2 delta x, so this will become 12, right? 6 and 6, so this would be divided by 2 delta x, so you would get something of the order of delta x square times partial cube phi by partial x cube, right? So that's what we would get. That means if I write this equation, what you get is partial phi partial x, which survives from here, plus delta x square by 6 dou cube phi by dou x cube. That's what we would get for this first quantity. Okay, now what we have to do is we have to also expand the phi north and phi south in terms of phi p, and then find out a value for phi north minus phi south by 2 delta y. Okay, that's what we would do. which I have not done, but which you can on a very similar lines by replacing delta x with delta y and partial phi, partial x with partial phi, partial y, and so on. You can show that phi north minus phi south by 2 delta y equals dou phi dou y plus delta y square by 6 dou cube phi by dou y cube, okay, and so on. So let us plug these two quantities back into the equation number 5. Okay, that means rho u times this quantity plus rho v times this quantity. Okay, so that is basically, if you substitute back, you get rho u times dou phi dou x plus delta x square by 6 dou cube phi by dou x cube plus rho v times dou phi dou y plus delta y square by 6 dou cube phi by dou y cube equals 0, plus and so on. There are several terms here. Now of course we can again rearrange this such that it looks somewhat similar to the original pure convection problem that we want to or wanted to solve, right? So let us kind of do the rearrangement. If we do the rearrangement, then it is rho u dou phi dou x plus rho v dou phi dou y equals, the remaining terms go to the right hand side, that is minus rho u delta x square by 6 dou cube phi by dou x cube minus rho v delta y square by 6 dou cube phi by dou y cube plus and so on, right? All right, let me also assume that, again for the sake of simplicity, I am assuming u equals v and delta x equals delta y, so that we can rewrite the right hand side, and of course the left hand side I am writing it as because rho u and v are constants, we can write it as dou x of rho u phi plus partial y of rho v phi equals, this would be, these two are the same, one and the same, so this will be minus rho u delta x square by 6 times dou cube phi by dou x cube plus dou cube phi by dou y cube. Okay, so that's what we have here. Now what is the leading truncation error here? It is second order accurate. This we already know, right? We know that the central difference scheme is second order accurate, right? That we already know, and but we wanted to solve for partial x of rho u phi plus partial y of rho v phi equals 0. But what we ended up getting is equation 6, which has some term here. This is not, we cannot call this diffusion because this doesn't have even order derivatives, right? This we would call in as dispersion, all the this term, and which is basically responsible for the oscillatory behavior of the central difference schemes. Okay, so in general, any derivative on the right hand side or in the modified equation that comes with odd derivatives, okay, so let me write it here. If it comes with odd derivatives, then we can call it as a dispersive scheme. Okay, so if there are odd derivatives appearing in the modified equation, then we can call this as a dispersive term. Again, we know that the dispersive term is basically of the order of delta x square. It kind of proportional to the grid size. So as we refine the mesh, the dispersive term goes smaller and smaller. That means we can expect the wiggles to become lesser and lesser, but nonetheless they will be there because the mesh is always something that is finite but small. Okay, so this is how we can now describe the behavior of the central differencing and the upwind difference scheme based on the terms that we get in the modified equation. Okay, essentially for this we got odd derivative terms which we are responsible for something known as dispersion, and for the UDS we got even derivatives which are similar to diffusion process, and as a result we can call UDS as diffusive process, diffusive scheme, and CDS as a dispersive scheme. Okay, so now of course you are also in a position to write a modified equation for any equation that will be given to you, right? For any equation, I mean essentially the process is construct the finite volume scheme, that is basically the construct the discrete equation, then use Taylor series expansion and substitute back for all the phi values at all the neighboring points in terms of phi p, and then rearrange it to look like the original equation, right? And then that is your modified equation, okay? And then you can analyze the modified equation and comment on what would be the solution be depending on the terms that you get in the modified equation, okay? So that is an explanation from the numerical point of view for the artificial or numerical or false dispersion and diffusion that we have seen when using CDS and UDS schemes in the solution of pure convection equation, okay? All right, so now let us move on to the unsteady convection equation. That means we are introducing the unsteady component. So that means if we go back to the general scalar transport equation, which is partial T rho phi plus del dot rho u bar phi equals del dot gamma grad phi plus s phi equal to 0, because we are only again interested in the pure convection but unsteady convection, we are setting these two terms equal to 0, okay? So essentially we are only interested in unsteady convection. So let us see, we also want to kind of make a simplification, so we will consider only a 1D scenario or a 1D situation, and then we also want to set the density equal to 1 everywhere. Then this equation can be written as partial phi partial t plus del dot, because it is 1D, you can write this as partial x rho u phi, right? Rho is 1, this is u phi equals 0. So this equation is known as in the literature as the linear wave equation, or it is also known as what? Linear advection equation. Now why is it linear? It is linear because u is known and is not a function of phi, right? That's why it is linear, okay? All right. Then what do we need to solve for this equation? This equation is basically a first order equation, and it has one time derivative, one space derivative, so it would require one initial condition, right? So this would require an initial condition, that is basically it requires a specification of phi 0 over the entire domain, that is the initial condition, and then it requires boundary conditions, right, at the both the ends of the problem, right? If you have a domain of length L, domain length is L, then we would need boundary conditions at x0 and xl, okay? Now what kind of an equation is this? This is a 1D linear advection equation. What is the type of this equation? Is it elliptic, parabolic, or hyperbolic? We have done this in the past, so this is basically hyperbolic equation, right? All right, so then for this equation, fortunately, exact solutions exist. So that is why we have chosen this equation, because this can help us understand how does the different schemes, the discretization schemes that we would choose behave when compared to the exact solution that we know, okay? So that means the exact solution to this linear advection equation is basically phi of xt equals phi naught of x minus ut. It's basically whatever is the initial condition, phi naught of x, that basically gets shifted by u times t, right? It basically gets shifted by minus ut, right, or ut essentially, and the shape as such of the initial profile would not change, right? That is preserved. That is the property of 1D linear wave equation. So whatever is the initial profile given, that initial profile will remain the same, but only thing is that there will be a shift of this initial profile to a different location depending on what is u and what is time by a distance u times t, right? Okay, that's what this says. Phi of xt at any time is nothing but phi naught of x. Instead of x you have x minus ut. So the shape would not change, but it only gets shifted, okay? All right, let us consider two initial conditions which are shown in black here, okay? So so one initial condition is basically using a sine wave, so this is at t equal to 0. Now at a later time, if you solve using 1D wave equation, the solution would come out to be something that is shown in red. Essentially, it will get shifted, but without a change in shape. Okay, it gets shifted by some distance. Now, how much is this distance? This distance is nothing but u times t, right? This is your u times t. Okay, after t seconds, it would have traveled u times t, but the shape as such remains the same. Okay. Similarly, if you take a square pulse, that is basically again shown using black at t equal to 0, this is the square pulse. Okay. Now this also gets shifted by a distance ut after a time of t seconds. Okay, so the red one is basically it goes this way, and the peak gets shifted. The entire initial condition gets shifted, but there is no change in the shape or size of the initial pulse, right? So the amplitude remains at 1.0. Same is the here 1.0 and minus 1.0. It's only a rigid body translation of the initial pulse. Okay, that is the exact solution that is given. Now this is very useful, because then we can now apply the different schemes that we were to work with, which are basically the upwind difference scheme and the central difference scheme, of course together with some kind of time stepping scheme for the unsteady term, and we can evaluate how does these schemes behave in this context, because we know the exact solution. We can compare it and see, well, do you see what it is supposed to be like from the numerical solution or not? Okay, so that kind of comparison can be done because the exact solution is known. Okay, so essentially the motivation is to see if the schemes that we would use that are constructed based on the upwind differencing and central differencing, can they predict the shift without introducing diffusion, that is the smearing out, or the dispersion, right? These oscillations or wiggles. So can we solve for these or not? So that is the question we can pose. Now that would be our discussion for the next lecture, essentially using central differencing and upwind difference schemes and some form of time stepping scheme. We would like to see what will be the solution that is obtained from these and compare it with the exact solution. Now this may look very simple because it's a 1D wave equation, it is linear. Well, will that be useful? Yes. Because of its simplicity, it is very extensively used in the literature to compare any new scheme that is introduced. However, the insights that we gain from working with this 1D wave equation can be useful in the more complex situations where we have nonlinear and coupled equations, such as in the context of Navier-Stokes equations. Okay, so what we learn from here can be directly useful there as well. So that is the motivation to study such a simple problem using the different schemes. Okay, all right, so I'm going to stop here, and we will continue with discretizing the unsteady convection equation using finite volume method and with different schemes in the next class. All right, thank you.